Hello class, today we're going to talk about lesson 4.3, writing functions. Our objectives are we can identify independent and dependent variables, and we can write an equation in function notation and evaluate a function for given input values. Let's look at our first example. We're going to use a table to write an equation. We need to determine a relationship between the x and the y values of this table so we can write an equation. So our x values are 1, 2, 3, and 4, and our y values are -2, -1, 0, and 1. Step 1 is we need to list some possible relationships that could exist between the first x value and the first y value. So what we need to do is we need to ask ourselves, how can we get from a +1 to a -2? Well, one way we could do that is by subtracting 3 from 1. So that's one possible relationship. Or we can multiply the x by -2. So we can go 1 times -2, which would also give us a -2. So either of those could work and do work for the first set of numbers. But step 2 is we need to determine if one of these relationships works for the remaining values or if the other one doesn't. So let's try that. So let's start by testing both relationships with our second x value. So if we go 2 and we subtract 3 from it, that does equal -1, which is the value we want. We could also go 2 times -2. 2 times -2 is -4. That is not the value we want, but we're going to still test this for every single point we have, just to make sure that they both work or they both don't. So if we go 3 and we subtract 3 from it, that does equal 0, which is what we want. If we go 3 times -2, however, that gives us a -6. That is not the solution we want. We've got one more to test, so let's try that out. If we go 4, take away 3, that equals 1, which is what we want. And if we go 4 times -2, that's going to give us -8. That is not the value we want. So it does appear that there is a clear relationship that does work, and there is one that does not. So step 3 now is we are going to write our equation. Now there are two things an equation, or a few things, in fact, an equation needs to have. We're going to have a y in our equation, and because equations sound like equals, we also need to have an equal sign. So y is going to equal. Now, we said we were taking a number and we were subtracting 3 from it. We're taking any number and subtracting 3 from it to work in our relation. Now, that any number we need to represent with a variable. We, in our table, are talking about x's and y's, so we will use x. So y is going to equal x minus 3, and now we have our equation for this table. Alright, here's a vocabulary alert for today. We are going to be talking about independent variables and dependent variables. All an independent variable is the input of a function. It's something that does not depend on anything else. While a dependent variable is the output of a function. It's the value that depends on the value of our independent variable. If we have an equation, typically our independent variable is the x, and our dependent variable is the y. So let's look at an example where we need to identify the dependent variable and the independent variable. Alright, so we need to identify the independent and dependent variables in each of the following situations. So we're going to start with A. In the winter, more electricity is used when the temperature goes down and less is used when the temperature goes up. So we need to think of what the situation is talking about. Well, the amount of electricity used is going to depend on the temperature. So with that logic, our independent variable is going to be the temperature, and our dependent variable is the amount of electricity, because the amount of electricity we use is going to depend on how hot or how cold it is outside. All right, let's look at another example. The cost of shipping a package is based on its weight. So the cost of the package is going to depend on how much that package weighs. So here, our dependent variable is the cost, because it's going to depend on our independent variable, the weight. We can't go to the post office and say, I'm going to pay $2 for this package without knowing how much it weighs. So the dependent variable is our cost, the independent variable is our weight. Let's check out one more example. The faster Ron walks, the quicker he gets home. So the time that it takes Ron to get home is going to depend on how fast he walks, or the speed that he walks at. So because the time depends on the speed, our speed is the independent variable and the time is dependent. Here's another vocabulary alert. We've got a function rule, which is just an algebraic expression that defines a function. And we've also got function notation, which is when x is the independent variable and y is the dependent variable, we can usually use the notation f parentheses x in place of y, where we read it as the f of x. Since our dependent variable is represented by y, we can say the dependent variable is a function of our independent variable, and our independent variable is x. So y is a function of x can be written as y equals the f of x. Let's look at an example where we are going to write a function. So we need to identify first the independent and the dependent variables, and then write a rule in function notation for each situation. So we have a lawyer's fee is $200 per hour for her services. Because the fee for the lawyer depends on how many hours she works, our dependent variable is the fee, and our independent variable are the hours. We can say that we want to let h represent the number of hours the lawyer works. So then in function notation, the function for the lawyer's fee is the f of h is equal to 200 times h, meaning that the fee that we will have to pay is going to be a function that's written in terms of the amount of hours we see the lawyer times $200, the lawyer's fee. Let's look at one more example where we are writing a function. So we have the admission fee to a local carnival is $8 and each ride costs $1.50. So here, the total cost depends on the number of rides ridden plus an additional $8. So our dependent variable is the total cost, and our independent variable are the number of rides that we go on. So what we can do is we can say let R represent the number of rides that have been ridden at the carnival. Then we can write the function for the total cost of the carnival as the f of R is equal to 1.50 times R plus 8. Now that means the function, or the fee, or the cost that we're going to pay in terms of the number of rides we go on at the carnival is equal to $1.50 times the number of rides we go on, because each ride costs $1.50 to go on, plus the $8 admission fee. So now let's evaluate functions. We're going to evaluate each of the functions for the given input values. We need to take the function f of x equals 5x and find the values of f of x when x is equal to 6 and when x equals 7.5. So let's start by finding the value of f of x when x equals 6. We are going to start by substituting 6 in for x. So we are going to write the f of 6 is going to be equal to 5 times 6. That is just simply substituting 6 in for x, and now we can simplify, do any of our order of operations that exist in this problem. We know that 5 times 6 is 30, which means that the f of x, or the f of 6, is going to be equal to 30. Now let's find f of x when x is equal to 7.5. So we have the f of 7.5 is equal to 5 times 7.5. Now we might not know what 5 times 7.5 is off the top of our head, but if we do the multiplication, we'll find out that f of 7.5, when f of x equals 5.5x, is going to equal 37.5. So we found the f of 7.5 and the f of 6. Let's look at another example. So we are going to take g of t where it equals 2.30t plus 10 and find the values of g of t when t is 2 and when t is negative 5. So let's start with t is 2. So we are looking for g of 2. So wherever there is a t, we are going to substitute a 2 in. So g of 2 is going to equal 2.30 times 2, and then we'll add 10 to that value. So now we can use our order of operations to simplify this. 2.30 times 2 is 4.6. So g of 2 is equal to 4.6 plus 10. Now if we add those two numbers, that means g of 2 is going to equal 14.6. So g of 2 is 14.6. Let's find g of negative 5. So we're going to look at g of negative 5 is going to equal 2.30 times negative 5 plus 10. Now 2.30 times negative 5 is going to give us negative 11.5. And then we add 10 to that value. Negative 11.5 plus 10 is going to result in negative 1.5. So to just recap that problem, we have plugged in negative 5 for t. We go positive 2.30 times negative 5, which is negative 11.5, and we add 10 to that number to get a negative 1.5. So g of 2 is 14.6, and g of negative 5 is negative 1.5. Let's check out one more example where we are going to evaluate a function. Alright, we're going to take h of x equals 1/2 x minus 3 and find out what h of x equals when x is 12 and when x is negative 8. So let's start with h of 12 when x is 12. So h of 12 is equal to 1/2. Wherever there's an x, we're going to substitute in a 12. So 1/2 of 12 minus 3. Now 1/2 times 12 is going to result in us getting a 6. And if we subtract 3 from that 6, we're going to get our final answer, which is h of 12 is equal to 3. So we have found h of 12. Let's look up h of negative 8. So wherever there's an x, we're going to substitute a negative 8 into the function. H of negative 8 is equal to 1/2 times negative 8 minus 3. 1/2 of negative 8 is going to give us a negative 4. And if we subtract 3 from negative 4, that's going to give us a final answer of negative 7. So h of negative 8 is equal to negative 7, and h of 12 is equal to 3. Alright, let's look at our final example, where we are finding the reasonable domain and range of a function. Manuel has already sold $20 worth of tickets to the school play. He has 4 tickets left to sell at $2.50 per ticket. We need to write a function rule to describe how much money Manuel can collect from selling tickets. And we also need to find a reasonable domain and range for the function. So let's start by just thinking of the situation we have. Money can be collected from ticket sales is going to be $2.50 per ticket sold plus the $20 Manuel has already collected. Now, because the amount of money we collect from ticket sales is going to depend on how many tickets we sell, the money collected will be our dependent variable and the number of tickets we sell will be our independent variable. So our money will be our y and our tickets will be our x. Now we are writing this in function notation, so we're going to say that the money collected from ticket sales as f of x is going to equal $2.50 times x plus 20. Or the function, or the money we collect as a function related to the number of tickets we sell is equal to $2.50 times the number of tickets we sell plus the $20 we've already collected. Now, if Manuel sells X more tickets, we don't know how many more he sells, but we'll use X to represent any number he could sell. We will have collected f of X equals $2.50 times X plus $20. Now, Manuel has only 4 tickets left to sell. So there are some logical numbers we can use for our domain. He could sell no tickets, 1 ticket, 2 tickets, 3 tickets, or 4 tickets. But he can't sell any more than 4 tickets. And he can't sell half of a ticket. So a reasonable domain for this situation would be the domain is 0, 1, 2, 3, and 4. Now to find the range of this situation, we can simply just substitute the values we found for our domain into our function rule, which is right here in this table. So if Manuel sells 0 tickets, we could go $2.50 times 0, which is 0, plus 20 to get a range value of 20. If he sells 1 more ticket, he could make a total of $22.50. If he sells 2 more tickets, he could make a total of $25. 3 more tickets, he could make $27.50. And finally, if he sells 4 tickets, he could make a total of $30 for the school. So a reasonable range for this situation could be written as 20, 22.5, 25, 27.50, and $30 in a list. That wraps up lesson 4.3 on writing functions. So for the rest of the evening, I would like you to do the your turn problems on your guided note sheets. See you tomorrow.